Good morning. In this section, we'll talk about our third topic, purification of organic compounds. Okay, purification of organic compounds. When we explain this topic, first of all, we should know what do we mean by purification. Okay, purification is a process done after doing any chemical reaction to purify our product. For example, if you do a certain chemical reaction in order to synthesize a certain drug or a certain active ingredient to be used in the pharmacy, okay? This chemical reaction will start by the reactants. A, for example, plus B will give C, okay? C is my aim, is my product that I want to put it in certain formulation to be sold in the pharmacy. But the question here, is C is the only product that will be produced? Of course not. With C, there will be something called impurities. C is not alone. Impurities will also exist together with C. Okay? And also there can be byproducts. Byproducts also can exist. Byproducts mean other products than C. Like D can exist, E can exist. Okay? So at last, C is not alone, is not pure. Together with C, there is impurities and there is byproducts. So can I take all this C with the impurities, with the byproducts, and put it in certain formulation to be sold in the pharmacy? Of course not. I only want C. I need pure C. Okay? So this is why we will do purification. We will get all these products. We will do certain purification steps in order to obtain pure C, to be able to make it a formulation in the pharmacy. Okay, so this is our aim. Purification is divided into two, depending on the type of material that I am purifying. Purification for solid material, okay, and purification for liquid material. Starting by liquid, how I can purify liquid? By a process called distillation. Okay, distillation is a process used to purify liquid compounds. Distillation. Distillation has many types, has 4 types. It can be simple distillation, okay. It can be fractional distillation, okay. It can be steam, and finally vacuum. 4 types of distillation that we will study together next, okay. Vacuum distillation has another subtype. There is a subtype of the vacuum distillation called the rotavap, or the rotary evaporator, and we will study all this by details, okay. Rotavap. Very good. So this is how we purify liquid by a process called distillation, and distillation has 3 types: simple, fractional, steam, vacuum, and there is a subtype of vacuum that is called the rotavap or the rotary evaporator. Okay. What about solid? Solid can be purified by 2 types. To ease memorizing them, solid start with S. Okay. So first type will be also by S. It is called sublimation. So first thing that I can purify solid with is sublimation. Okay. Okay. S, the alphabet that is very common to us is the C, S and C. So you use C, and we will say our second method for purification of solid is called crystallization. Like I told you, SS and SC to ease memorizing them. Crystallization. Okay. Very good. So this is what we will study in this section. First of all, we will talk about distillation. That is a method to purify liquid compounds. We will study all the types of it. And after this, we will talk about purification of solid by 2 techniques: sublimation and crystallization. This is the theoretical part. And also I want to tell you that next section, okay, the next section, we will work practical work, the crystallization. So we will do crystallization practically in the laboratory, okay. So this is the only technique that we will work it in real, in the lab, practical work, the crystallization. Okay. Okay, very good. Okay, let's carry on. First, we said we are going to talk about distillation. Distillation, we said it's a method that is used to purification of what? Of only liquid compound. Okay, let's explain distillation. Any distillation process composed of two important steps. Two steps. This is the aim or the essential steps of any distillation process. First step is called evaporation. How this step is performed? First of all, we have the liquid, okay, that I want to purify. This is the liquid. I want to do evaporation, okay. How I can evaporize a liquid? Of course, by using heat. So I need heat. I need here to put source of heat, flame or anything, source of heat, okay. So liquid, when it is heated, when it's reached boiling point, it will be converted into what? Into gas. Yes. So this is our first step. It's called evaporation. We convert liquid into gas by using source of heat. Second step is the opposite of evaporation and called condensation. Okay. What do we mean by condensation? Here we obtain the gas. We bring our gas and we need to convert it into liquid again, return into liquid. So this is condensation. The gas will be returned into liquid. In order to do this, we need source of cooling source. Okay, totally the opposite. Here we need source of heat, but here we need cooling source. Okay, very good. So this is our two main steps in any distillation process. First of all, my liquid will be converted into gas by evaporation by using source of heat, and condensation, gas will be returned into liquid by source of cooling. But what's the benefit of this? First of all, this liquid, is it pure liquid? We said no, this is a liquid that I need to purify. So this liquid contains impurities. Okay? But this liquid, the end product will be pure liquid. So this is our main difference between those two processes. Pure liquid. The liquid that I started with, it contains impurities. It is impure. But after converting it into gas and condensing the gas into liquid, this liquid at the end will be our pure liquid that I can use it for any formulation. Okay, let's explain this in diagram. Okay, we will explain this process in diagram. First of all, in order to do distillation, we need a flask, conical flask. What we will put in this conical flask? Our liquid. But we said the liquid is not alone. It also contains what? The impurities. Okay, so this flask will contain the liquid. Here, the liquid and impurities will be in this flask. This flask is called distilling flask. Okay, it's called what? Distilling flask. Okay. Okay, so this flask is called the distilling flask. Okay. Now I need to put the source of heat. The source of heat will be a certain flame that I will put it here. Okay. I will put here certain flame. What will happen to our liquid by using this flame? It will be evaporized to give us the gas. Okay. In order to obtain this gas, I will put here closed system, certain tube, and I will close this very well in order to prevent the gas from leaving out. And this tube will carry on the gas. So the gas will get up in this tube. Okay, this is the gas will get up here in this tube, and I will put here certain thermometer to be able to monitor the temperature. Okay, thermometer. Here is the thermometer, here is distilling flask, and here is the gas in closed tube. Like this, I finished first step. It is evaporation. Let's move on to the second step, condensation. We said in order to condense the gas, we need a cooling source. We need to put a cooling source. This cooling source will be the water jacket. I will put here another tube a little bit larger, and this tube will carry on water, cooling water. This will be the water inlet. Okay, and up here will be the water outlet. Water enter from here and leave from here. Why not the opposite? Because when water enter from here and leave from up here, it will be walking inside against the gravity, and this will slow down a little bit the water, and this will be more better in order to get efficient cooling and efficient condensation. But if water enter from up here and get out from down here, it will be moving with gravity, and this will speed up the process of water to leave, and the cooling will not be efficient. So it is very important that water inlet will be from down here and water outlet from up here to be able to move against the gravity. Okay, this cooling water will convert this gas into what? Into liquid, and I will receive this liquid here. So gas, when it is in contact with this cooling water, will be converted into liquid. Will be converted into liquid, and liquid will be received here. Okay, this is my liquid, will be received here in certain flask. We'll call it receiving flask. Means the flask in which we receive the liquid. Receiving flask. Okay, yes. And like this, our second step has finished. Gas here by certain cooling source, it is the water jacket here, will be converted into liquid that will be received in this receiving flask. This part is called, all this part is called condenser. Okay, yes, very good. But this liquid, the liquid in the distilling flask, it was impure liquid, liquid with impurities. But the liquid here in the receiving flask, it is pure liquid. So this is very important difference. Okay, the liquid in the receiving flask, pure liquid, but the liquid and first in the distilling flask is impure. We said it may contains impurities or other byproducts. So this is the chart or the diagram of distillation. Okay. Okay, now we should move to the type. We said this was the explanation of a distillation as a general process, but we said there are 4 types: simple, fractional, steam, and vacuum. Before we starting them, I want to talk a little bit about something called the boiling point. Okay, the boiling point. What is the boiling point? It is very important. Boiling point, as a definition, it is the temperature at which the vapor pressure, you can write after me, it is the temperature at which the vapor pressure of the liquid, vapor pressure of liquid, will be equal to the external pressure. When the vapor pressure of the liquid it is equal to the external pressure, at this temperature liquid start to boiling and start to be converted into gas. Okay, let's simplify this. When we have a certain cup of water, cup contain water, and we will leave this cup at room temperature. Room temperature, for example, we can set 25 or 30 degrees Celsius. 25. At this temperature, can water be evaporated? Of course no. It stay as liquid. What happening at this temperature? Even it is not the temperature of boiling of water, but water will produce certain amount, very small amount of vapors. Okay. Even at 25 degrees Celsius, it will produce unseen vapor, very small amount of it. These vapors will produce what? Will produce a pressure, and this is called the vapor pressure of the water. So at this temperature, it produce a little amount of vapor. It will be called the vapor pressure, and its direction will be up, like this. Pressure, up pressure. But against this pressure, it will be what? The other pressure, the external pressure. This external pressure will be at opposite direction, from up to down, like this, and it will be equal to the atmospheric pressure. Okay, atmospheric pressure. At this stage, at 25 degrees Celsius, which pressure is the strongest? Of course, the external pressure is strongest. This external pressure will be far more strong than this small vapor pressure. So water remains as liquid, okay? Because the up pressure is stronger than the down pressure, and so liquid or water remain as liquid by the action of this pressure. So in order to vaporize or to reach the boiling point, I can do one of two steps, okay? First thing I can do to vaporize the water is to increase the vapor pressure. This small vapor pressure, I want to increase it in order to reach and to be equal to this strong external pressure. If I can do this, water will start to boil. So by increasing vapor pressure, write it again. Where is this pen? So first thing I can do to vaporize water is to increase vapor pressure. Okay. Or I can do something else. I can decrease the external pressure. Okay. So I can vaporize water by increasing the vapor pressure or by increase vapor pressure or decrease the external pressure, decrease the atmospheric pressure. How I can do this? First thing, to increase the vapor pressure easily by elevating or raising the temperature. Increase the temperature. When I increase the temperature, what will happen if the temperature will be 40, 50, 60? The vapors produced by water will increase, will be here a lot of vapors, and so the vapor pressure here will also increase until it reaches the external pressure. When I reach 100 degrees Celsius, okay, this vapor will produce certain vapor pressure. It will be equal to the external pressure, and at this temperature water start to boil. So at 100 degrees Celsius, the amount of vapor here will produce certain vapor pressure which will be equal to the external pressure, so water start to boil. So first thing, by increasing temperature. Is there another way to increase the vapor pressure? Is there another way to increase the vapor pressure and not by increasing temperature? Yes. And this way will be used for thermolabile material. If I have certain thermolabile or thermosensitive material, I cannot raise the temperature very high. So what I will do to reach its boiling point, I can raise the vapor pressure. Okay, I can raise the vapor pressure, and by not increasing the temperature very much. How I can do this? By adding another liquid. Yes, this is very important step. Adding another liquid. How is this? How this will happen? Okay, when I add another liquid together with water, okay, the amount of vapor produced will be increased because it will be the amount of vapor of water plus the amount of vapor of another liquid. So the vapor pressure will be increased at the same temperature by not raising temperature, by not getting or by not changing the temperature. So when I add another liquid, the amount of vapor produced here will be the sum of the vapor of the water and the vapor of the liquid. So this vapor pressure will be increased by not changing the temperature. So this is very important. So there is a very important rule. It said when we have a mixture of two liquids, when I have a mixture of two liquids, the boiling point of this mixture, it will be below the lowest boiling point of the liquid. For example, this is very important. I want you to write it. When I have a mixture of two liquids, the boiling point of this mixture will be lower than the lowest boiling point of the two liquids. For example, if I have certain liquid, its boiling point at 160. I will put with this liquid water. What is the boiling point of water? It's 100. If I mix those two liquids, the boiling point of the new mixture between liquid and water, what is the boiling point? It will be lower than the lowest boiling point. So it will be lower than 100, for example, 80 or 90. Look, a very different change. This liquid was boiling at 160. By mixing it with water, this mixture will boil at 80 or 90. A huge difference between this. Why? Because the amount of vapor increased by the action of liquid and water. So this is our second thing that we can use to increase vapor pressure by not increasing the temperature. What else I can do? I can decrease the external pressure in order to reach the vapor pressure. How I can decrease the atmospheric or the external pressure? By putting something called vacuum. Something vacuum pump that will absorb or take the air, so it will decrease the pressure. So by using vacuum, those those two methods, adding another liquid or vacuum, are used for what? For thermolabile material, in order to vaporizing it or reaching its boiling point without raising the temperature so much to prevent destruction of the material by the temperature. Thermolabile material, okay? So raising temperature, it is used for thermostable material, but adding another liquid or vacuum, it is used for thermolabile or thermosensitive material. Okay, this is very important because we will use this concept in the next types of distillation. Okay, let's now take the different type of distillation. We said the first type is a simple distillation. From its name, it is very simple. It contains the same components that we explained in the diagram. Okay, simple distillation. What we will study in this distillation first, as a type of liquid it is used for. Simple distillation. Okay, we can open the PDF. Okay, this is what we are talking about: vapor pressure distillation. Simple distillation, it is used for two types of liquid, for separation of pure liquid from non-volatile impurities at atmospheric pressure, and it is used for separation of pair of liquids whose boiling point differ by 50 to 70. Those two should be studied very well. Let's talk about first one. It's telling you that you have a volatile liquid, is this distilling flask, together with non-volatile solid impurities or non-volatile impurities. What will happen when you heat? Only the volatile liquid will be vaporized, but the volatile or the non-volatile impurities will remain in the distilling flask because they are not volatile. The liquid will get up here as the gas, and gas will enter in the condenser. It will be cooled by the cooling water, then converted into liquid again, and liquid will be received here as pure liquid in this receiving flask. Okay, in this case, when you have a pair of liquid whose boiling point differ by 50 or 70, if you have, we can explain this, 50 or 70 at least 50 or 70 degrees Celsius. If we have pair of liquid, one will be boiling at 300 and the other will be boiled at 360. So the difference is 60, so it is very good. When I raise the temperature to reach 305 or 310, which liquid will be boiled and will be converted into gas? Only this liquid will be converted into gas. So it will be converted into gas in the condenser. It will be condensed into liquid again, and it will be received in the receiving flask. But this liquid will remain as it in the distilling flask. Like this, I can obtain all the first liquid here. If I want to obtain again the second liquid, I can change the receiving flask, put another flask, and I will raise the temperature to reach 360, 370, 380. So this liquid will also start to boil, will be converted into gas, and by the action of the condenser will be returned in the liquid, and I can receive this second liquid in the next or in the new receiving flask. So by this technique, I separated the two liquids. The first one will be obtained in the first receiving flask, and the second one is obtained in the second receiving flask. Okay, so this is simple distillation. Second type, we said it is a fractional distillation. In this type of distillation, we can separate two liquids. The difference in their boiling point is not from 50 to 70, it's only few degrees, from 5 to 8 degrees. How I can do this? By adding something called packed column. We will put additional condenser. This is an extra part that will be put in the fractional distillation, an extra part. It is called the packed column. It is column packed with glass beads, pieces of glass. What is the function of this packed column? I told you, if you have two liquids, the boiling point, the difference, the boiling point is only a few degrees, like 300, and the other will be 305. If I'm using this in the simple distillation without the packed column, if I reach 302 or 301 or 303, this liquid will be vaporized and will be converted into gas, strong gas. And also this liquid at this temperature that is very close to its boiling point will be also converted into gas, but a smaller amount, not all the liquid. So if the two liquids will be converted to gas, this will be all converted into gas, but this small amount. So after this, those two gases will be condensed in the condenser, and I will receive them in the receiving flask. Like this, in the receiving flask. Do we have a pure liquid? No, we have a mixture of both liquids, so I cannot do this by the simple distillation. But in case of packed column or fractional distillation, there will be something called packed column with glass beads. So when this liquid starts to boil at 302, it will give a strong vapor or strong gas that can be able to pass this packed column. It will not delay it, it will pass it and reach the condenser. But this liquid at 302, it will be produce vapor, but in very small amount, in very small speed. So these vapors of the second liquid will be delayed here, cannot pass through the packed column. It will be delayed by the glass beads, and it will stuck here. It will be stuck here in the packed column. And these glass beads, it is cold glass, so it will be condensed, and the gas of the second liquid will be returned into liquid and will return again to what? To the distilling flask. Okay, so the function of the packed column is to delay. This is very important. The function of the packed column in fractional distillation is to delay and condense the vapor, the small amount of vapor of the second liquid, to return again to the distilling flask, in order to obtain only in the receiving flask the first liquid. Because the first liquid, the amount of vapor is very strong, it will not be delayed by the packed column. Okay, after this, after obtaining all the first liquid, I will change the receiving flask, and I will raise the temperature to reach 305, 306, 310, 320. So the second liquid will be able to produce certain amount of vapor that will pass the packed column and reach to the receiving flask to obtain pure second liquid. Okay, so this is very important. It is used for two liquids, few degree, and by using this packed column. Third type is steam distillation. Okay. Third type is the steam distillation, and the steam distillation is used for thermolabile material. The first two types, the simple and the fraction, was used for thermostable material, but steam distillation is used for thermolabile material. Remember, I told you when I have a thermolabile material and I want to reach its boiling point, I cannot raise the temperature because the temperature will destroy our material because it is thermosensitive or thermolabile. What I can do in order to reach the boiling point without raising the temperature so much, we said there is two methods, we explained them. The first method was by adding another liquid in order to increase the vapor, amount of vapor, and the mixture will be boiled at lower of the lowest boiling point of the two liquids, or by adding vacuum. In this type, steam distillation, we will add another liquid. What is the another liquid? Is water. We will add a steam of hot water. So together with my liquid, I will add a steam of hot water, but there is a condition that this method should be only used for heat sensitive or thermolabile materials that are immiscible with water. They must be immiscible. Why? We will explain this. Okay, what is the advantage? The temperature never exceeds the boiling point of water because we said the mixture will be boiled below the lowest boiling point. So again, steam distillation is used for thermolabile liquid that is and must be immiscible with water. What is the new part that we'll put? This is the new part that we'll put in our device on our diagram. It is the pump that will pump us hot water here. So in the distilling flask, it will be the mixture of two liquid plus water. So the boiling point of this mixture will be lower than the lowest boiling point. It is the boiling point of water. It will be boiled at, like we said, at 80 or 90. When I raise the temperature, both water and liquid will be converted into gas. Here, the gas of water and liquid will be condensed. Here, I will receive water and my liquid in the form of liquid after the condensation. But here, if I stop here, the liquid here, is it pure? No, it is not pure because it contains also the water. I want to separate my liquid from water. So this is why we said that our liquid must be immiscible with water in order to form here two layers, so I can separate them by using something called separating funnel. Yes, because they are immiscible, the liquid is immiscible with water, I can separate it from water in the receiving flask by using this separating funnel. But if the liquid was miscible with water, I can never separate it, so we must use liquid that is immiscible with water. Okay, if the liquid is miscible with water, I cannot separate it from water by using this separating funnel or by using any other device. So this is why it must be immiscible with water. Okay, so this is steam distillation for thermolabile liquid immiscible with water. What is the extra part that we put? It is the pump of hot water that pump here water together with liquid. Okay. The last type, it is the vacuum distillation. From its name, it is very easy. Also used for thermolabile material, but it can be miscible with water. So this one used for thermolabile material miscible with water. How I can reach boiling point of thermolabile material by not raising the temperature? I will put vacuum. We said the vacuum will decrease the external pressure, will decrease the atmospheric pressure in order to ease reaching the boiling point. Okay, like we said, vacuum will reduce the pressure, lowering the boiling point. Two type of vacuum: water pump vacuum or rotary oil pump vacuum. You should not study this. Okay, this is not for studied, only for reading. Okay, you should only know that we put a vacuum, and this vacuum will be used for thermolabile material that is miscible with water. Where I put the vacuum, here is the vacuum. Okay, you should know that this part of the diagram, it is the extra part, put it here, it is the vacuum. Okay, this is the part of the vacuum that will take the air and decrease the atmospheric or the external pressure. So to revise this, first type, simple distillation, it is the same device. We do not put any extra part, used for used for volatile liquid with non-volatile impurities, and two liquid volatile, difference in their boiling point from 50 to 70. Second type, it is the fractional distillation, used for two volatile liquids. The difference in their boiling point is few degree by using an extra part, which you should know this extra part. It is the packed column with glass beads. Third type is the steam distillation, used for thermolabile liquid but must be immiscible with water, and we add an extra part. It is the steam of hot water, the pump that pump us steam of hot water, and we said that I can separate the liquid from water by using separating funnel. Last type, it is the vacuum distillation, used for thermolabile liquid, but it can be miscible with water by adding an extra part. It is here, this part, it is the vacuum source or the vacuum pump. So this is what you should study in those four types. You remember we said that vacuum distillation has a certain subtype called the rotavap or the rotary evaporator. The rotavap, it is a special type of vacuum. It is used. What is the rotary evaporator? It is something that will be attached to our distilling flask that make it turn, that making do like shaking, turning it rotary, or making a rotation for it. When I rotate the distilling flask, this will speed up the process of distillation. So it is very useful when I use this for the removal or the distillation of large amount of solvent. When I have large amount of liquid or large amount of solvent that I want to distillate, if I will not use this rotary evaporator, it will be happening very small. Okay, it will be take a long time. But by using these rotary evaporators that make the distilling flask rotating, it will speed up the process and decrease the time consumed. So again, rotary evaporator, it is a special device that is attached to the distilling flask in the vacuum distillation. What is its function? It is used for the rotation of the distilling flask to speed up the process or to decrease the time consumed when it's used for a large amount of volatile liquid or large amount of solvent. Okay. Okay, so this is the rotavap or the rotary evaporator. Okay, like this, we finished the first half of our section. It is the purification of liquid compound. We purified them by only one technique, distillation. Now we will go on to the purification of solid compound. We said that there are two methods, sublimation or crystallization. Okay. Okay, let's talk about purification of solid compound. First method is sublimation, very easy method. What is sublimation? Sublimation is the operation of converting solid compounds into gas compound directly. The normal process is converting solid first into liquid by melting, then converting liquid into gas by evaporation. By sublimation, skip this. It converts solid into gas directly without passing through liquid state. No liquid state will be here. Solid will be directly converted into gas. No liquid state or no melting will happen. So again, sublimation is the process of converting solid material into gaseous material without passing through liquid state or without melting. This method is very good for purification of solid compound. This is only what I need you to study in this method. Okay, we should not memorize the example here. In the PDF there is certain example. I think like if yes, you should not study these examples. Okay, it is only used, we can say that sublimation can be only used for sublimable solid. Not all solid have these properties. Not all solids have the property of converting them into gas directly. So it is only used, you can study this, only used for sublimable solid. Any sublimable solid we can perform sublimation to purify it. Okay, but you should not memorize the examples. Any sublimable solid. Okay. Very good. This is the first type and we finished it. Okay, let's move to the second type. It is the crystallization, and I told you the crystallization we will study it theoretically this section, but next section it will be worked practically in the lab. Okay. Okay, last thing we'll talk about its crystallization. Okay, let's explain it. The process of crystallization, we said that is used for purification of solid compound, has two aims. Okay, first aim is to separate, okay, separate my organic compound, my solid organic compound from impurities. So separate from impurities. My organic compound, the solid organic compound, will also contain certain impurities. I want to separate it from it. Okay. Okay, this is first step. After separating my organic compound from impurities, I want to obtain it in the most pure form of solid compounds. The most pure form of solid compound is the crystal form, and it's come from the name of the process, crystallization. So I need to obtain crystals of my solid, not only precipitated or solid particles. I must obtain crystals of my solid compound because the crystals are the most pure form of solid. Crystals of my compound of solid. So let's see how I can achieve those two aims. First of all, let's take certain example. If I have, and this is the example that we'll work with next section in the lab. Okay, if I have a mixture of salicylic acid and charcoal. Okay, salicylic acid and charcoal. Salicylic acid is considered my product, but charcoal are considered what? The impurities. So what is my aim? I will perform crystallization for them. The first aim, I want to separate salicylic acid from charcoal, like we said here, separate from impurities. After this, when I separate salicylic acid from charcoal, I want to obtain this salicylic acid in the most pure form of it. It is the crystals, and he has a very characteristic needle-shaped crystal. So let's see how I can achieve those two. First of all, in any crystallization process, I should pick or choose a certain solvent. Okay, this is the first thing that I should do in any crystallization process, to pick a certain solvent. This solvent has a specific property. What is its property? Let's write this first, cold and hot. It's telling you that the solvents that I must choose to solubilize our compounds must not solubilize my product on cold, but it can solubilize it on hot. And it will not solubilize our impurity either on cold or on hot. This is very important. So the solvent chosen in any crystallization process must solubilize my wanted compound only on hot, not on cold, and will not solubilize the impurities either on cold or on hot. This is very important. What is this solvent that can be used here that has this property? It is the water. The water can solubilize salicylic acid only on hot and cannot solubilize charcoal either on hot or on cold. Okay. So what I will do? First of all, I will bring a beaker. Okay, let's write it here. I will bring a certain beaker. This beaker will contain the salicylic acid and the charcoal. Okay, and I will put in the beaker the water. I will put here water. If I do shaking after putting water, if I do shaking on cold, is there anything that will be solubilized? Of course not, because when I am on cold, shaking here will be on cold. When I am on cold, neither salicylic acid nor charcoal will be solubilized. So on cold, nothing will happen. So what I will do, I will heat the beaker. I will put the beaker on the direct flame. Okay, like we do in the section, like we heat any beaker. After heating it, what will happen to the solution of the beaker? We said after heating on hot, the water can be able to solubilize salicylic acid, but it not solubilize charcoal. So here I will have a solution. Solution will contain what? Will contain two things. This solution will contain two things. Will contain salicylic acid and water, right? And there will be also the charcoal that will be precipitated, that is not soluble in the water. So now in the beaker I have two things: solution containing salicylic acid solubilized in water and charcoal. How I can separate this solution from charcoal? Of course, to separate any liquid from solid impurities, we do filtration. So next step is filtration. We'll bring our filtration set conical flask, and a funnel, and we put in the funnel the filter paper. Any filtration set consists of three parts: conical flask, funnel, and filter paper. And I will pour this beaker into this filtration set. What I will obtain, okay, on the filter paper here will be the solid, not solubilized material. It will be the charcoal. So the charcoal will be obtained here on the filter paper, and down here, what will be down here? The solution or our filtrate, that is salicylic acid plus water. Okay, so by this I achieved our first target. Remember, I told you our first target is to separate my compound from impurities. So now I was able to separate my compound from charcoal. Charcoal will be here on the filter paper, but my compound will be here together or solubilized in water here in the conical flask. So this is how we achieve our first aim. Let's see how I can achieve our second aim. Uh, is my compound not now in a pure form? No, I want to my compound now is soluble in water. I cannot see it. It's not solid anymore. It is soluble in water. So I want to first of all separate it from water or precipitating it from water, and then obtaining it in the form of crystal. How I can perform this? Can you think with me? Now my compound is soluble in water. How I can separate it from water? I want it to precipitate from water. Remember, we said the solvent used, this water, only solubilize in my compound. In which condition? In hot. So if I bring this conical flask or this solution and I make it cool or make it cold, if I cool it, what will happen? If I cool it, immediately my compound will be separated from water, because water cannot solubilize my compound in cold condition. So if I bring this conical flask and I cool it, my compound will be separated from water. Okay, so this is very important. But this is not my aim. I want it to precipitate or to be separated from water, not in the form of normal solid particle, but in the form of what? Crystals. So how I can achieve this? Let's see. Okay. Again, in order to separate my compound from the solvent water, I should only cool it. If I cool it, my compound will be separated from water and will be precipitated, because it is not soluble in water in cold condition. It is only soluble in hot condition. But this is not the only thing I want. I want to separate, I want my compound to be precipitated from water, but in form of crystals. How I can do this? It's telling you there is two types of cooling. Okay, the cooling that I will do to the solution are two types. First type is the fast cooling. Fast cooling, we can call it also forced cooling. I force the compound to be cooled. This one can be achieved by shaking the compound or the solution, or putting it under water, or putting it in ice. This fast cooling or forced cooling will not be able to produce crystals. Crystals cannot be produced fastly or by forced cooling. So this one will produce solid particle, not crystals. Solid particle, or we can call it impure broken crystals. It will be broken small crystals, not the needle-shaped crystals. Okay, so this is very important. If I will do fast cooling or forced cooling by shaking the conical, or by putting it under water, or by putting it in ice, this will be forced cooling. It will never produce crystals. It will only produce solid particles or impure broken crystals. So what I can do, of course, I should do, in order to obtain the needle-shaped crystals, I must perform slow cooling. Okay, slow cooling. How I can perform this slow cooling? It will be only air cooling. I will leave the conical flask without touching it, without moving it, only on the bench, to be able to cool it by air, only by air. This is very important, and we will perform this next section. We will leave the conical flask on bench for air cooling without touching or moving it. This air cooling will allow my compound salicylic acid to be separated from water in form of crystals, of needle-shaped crystals. Very important, needle-shaped crystals. So this is our target. If I will do this slow cooling, my compound salicylic acid will be precipitated and separated from the water, but in form of what? Of needle-shaped, very characteristic needle-shaped crystals. And we will show this, and we will see this next week in the section. Okay, like this, I was able to achieve my second goal. It is to separate salicylic acid in the form of crystals. Okay. Okay, this is the theory of crystallization. It is very important. I want you to memorize it very good, because we will work this next section. Last thing I want to say, we talk rapidly about something called melting point. Melting point, what is melting point? It is the temperature at which solid will be converted into liquid. So again, melting point, it is the temperature at which solid will be converted into liquid. It's telling you when you have impurities. Again, we were talking about melting point. I told you melting point, it is the temperature at which solid will be converted into what? Into liquid, melting process. When I have the solid together with impurities, there are two cases of melting point. And when I have pure solid, what is the difference between those two melting points? When you have a pure solid, the melting point will be sharp, will be a sharp number, only one number. For example, 30, sharp number. And it will be a little bit higher in comparison with solid with impurities. So when I have solid with impurities, its melting point will be a range, not a sharp number, a range. It can be ranging from 25 to 30. Any degree Celsius of this can melt it, but here it must reach 30. It is sharp in pure solid, but is in solid with impurities, it will be a range. Also, here it will be higher, a little bit higher than here. Here it will be a little bit lower. Lowering impurities. Okay, so impurities that exist with my solid compound can do two things to its melting point. It will convert the melting point either from sharp number into a range of number, and it will lower, very important, it will lower our melting point. For example, here it was 30, but here it is from 25 to 30, a range, and it is a little bit lower than 30. Why is this? Because impurities exist between the intermolecular spaces of solid. So in order to convert any solid into liquid, I want to separate the solid from each other. The existence of impurities is this separation, because the impurities exist in the intermolecular spaces between this solid, so it is their separation. So this is why it's lowering the melting point and make it inert. So after performing crystallization, first of all, if I measure the salicylic melting point of salicylic acid with charcoal together, it will be a range and it will be a lower number. After performing crystallization, to make sure or to validate our crystallization process that I obtained the pure salicylic acid, when I measure the melting point, I should found a sharp melting point, not a range, and it will be a little bit higher than measuring it before crystallization. Okay, so in order to validate the crystallization process, I should measure the melting point before crystallization and after crystallization. Before the crystallization with impurities, it will be a range and it will be a little bit lower number, but after crystallization, it will be a sharp melting point degree Celsius, and it will be a little bit higher because we get rid of the impurities. Okay, so this is our last thing I want to talk about. Okay, we will, like I said, we will work this process, the crystallization process, practically next week in the section. Okay, goodbye.